Good morning, everyone, and welcome to today's class. Today is a continuation from where we stopped in our previous class. We had started the statistical inference on single regression coefficients, and we looked at the various ways of defining the null hypothesis and also the alternative hypothesis, and also how to calculate the t-statistic and how to make a decision. Okay. So today I want us to look at the use of p-values, and the word p-value here is just the short form of a probability value. P-value is a probability value. It's the short form of the probability value, the p-value, okay? And we start by saying that this is an alternative way. It is an alternative way. Instead of using the tables, instead of using the tables, the table values of testing the significance of parameters or test statistics. So it's an alternative way of testing the significance of parameters or test statistics. And we can define it as, it is defined as the smallest significance level, the smallest significance level at which the null hypothesis could be rejected, at which the null hypothesis could be rejected. So let me use a diagram to illustrate that, it will be more clear. So for instance, if you are doing an upper tail test under the normal distribution, this is your 0, and then this is your t calculated. If that is your t calculated, for instance, then the p-value is this probability. That is what you call the p-value, that one. That is your p-value. That is your p-value. If you are doing a lower tail test, and then this is your, can even call this one Z now. If this is your Z calc, please notice that that is Z calculated, not critical. Here we don't use critical values. So this value here, this area here, or this probability is what we're calling the p-value. It is the smallest level of significance at which we can reject the null hypothesis. If you have a two-tailed test, on the other hand, if you have a two-tailed test, you have something like this. Then the sum of this, so this is your calculated value. Let's call it t calc, and this is also t calculated. Then a sum of these two areas is what gives us, so sum of these, the p-value. The p-value. So it gives you, it tells you the amount of evidence that you have against the null hypothesis or in support of the null hypothesis. Usually it's the amount of evidence you have against the null hypothesis. Okay? So if the evidence is very, very small, if the evidence you have in support of the null hypothesis is very, very small, then you reject the null hypothesis. You reject the null hypothesis. So we say that if the p-value, if the p-value is smaller than the chosen level of significance, we say that level of significance is also denoted by alpha. So we reject the null hypothesis. We reject the null hypothesis. Okay. So the general rule, let me be repeating that. The rule is reject the null hypothesis for small p-values. Reject the null hypothesis for small p-values. And what we are calling small p-values is defined by this. If the p-value is smaller than the chosen level of significance. For instance, e.g., if you are using alpha is 5%, you reject H naught when p-value is less than 0.05. That's the rule. Okay, so if alpha is 1%, you reject H naught when p-value is less than 0.01, etc. etc. So it's like the evidence you have in support of the null hypothesis. If the evidence is very small, you reject the null hypothesis in favor of the alternative hypothesis. So let's consider, no, before we do that, let's note that when you're using the computer generated output, you have to be cautious. So we say that computer output contains p-values for the null, contains p-values for the null for the null hypothesis that the coefficient is 0 and the alternative hypothesis that it differs from 0. So it's good to be careful about that. When we are using computer output, it's good for you to note that does not apply. The p-values given there are for a very specific null and alternative hypothesis. Okay, so this is the hypothesis that is whose p-values are given when you use the computer. So you have H naught at beta j is equal to 0 versus H1 that beta j is different from 0. So the computer gives you p-values to test that hypothesis only. So if this is not the hypothesis that you are testing, then you need to apply this idea here. Once you get the calculated T statistic or Z statistic, you place it here, then you can read out these values. If you know, for instance, if your T calculated is 2, if your T calculated is 2, let me call it Z for simplicity. If this is 2, so this is 0, and this is your Z calc, which is 2.0, for instance. The p-value is the remaining area up here. You'll need to use your tables. You'll go to your tables, and then you'll find the remaining area there. So let's quickly do that. All right, so when you use the normal tables, you'll observe that the area from 0 to a Z value of 2.0 is 0.4772. 0.4772. And the p-value is the area above that. So the p-value is 0.5 minus that, which is this. So if you are making decisions, if alpha was 5%, this is the same as 0.05, you would compare this value and this value. You compare them. So in this case, we'll argue that p-value is less than 0.05. So that means that you reject the null hypothesis. So that's how you make conclusions there. If the p-value is small, and this means smaller than the level of significance given, you reject the null hypothesis. Okay. So if it were on the left-hand side, you would do the same thing. If you were talking about, let's say you have something like this, and then your calculated value is, for simplicity, let's work with a z value. So z calc is minus 1.85. That's what you calculate, for instance. So your p-value is the area below here. Okay, so usually the p-value is the area of getting a value which is bigger than the absolute value of the calculated statistic, or let's say probability that of getting something larger than, bigger than z. This is t calc, and this is z calc. Getting something larger than, or getting a statistic larger than what you have observed, or more extreme than what you have observed, is what we call a p-value. So in this second scenario here, you would come to your tables, look for 1.85, 1.8, 1.85. So you have 0.4678. So that is 0.4678. Remember, the areas are from the center all the way to the given value of z. Okay. So the remaining area is your p-value. So you have 0.5 minus 0.4678, which is again a small p-value. So this is 0.0322. So you make a conclusion based on that. So basically, that's how you obtain, if you wanted to obtain the p-values, that's how you would obtain them. But if your hypothesis, if the hypothesis being tested is this, you use the computer generated p-values to make your decisions. Okay, so I want us to look at one of the examples that we did last time, which has p-values. Then we can make inferences about the p-values there. About the regression coefficients there. So here is an example of an output. So we can use the p-values to make inferences about the regression coefficients, and we'll use the last column here. The last column here, the p-values column, will help you to know whether the regression coefficients are significant. So by default, alpha is 5%. So you're going to reject the null hypothesis that H naught, that beta j is equal to 0, in favor of H1, that beta j is different from 0 if your p-value is less than 0.05. So in the first case, the intercept, you see that the p-value is very, very small. It's by far less than 0.05. So we reject the null hypothesis. We reject the null hypothesis. Then the second one, education, we also notice that the p-value is very small, very close to 0. So that means that we have a lot of evidence against the null hypothesis. We have a lot of evidence against the null hypothesis, or very small evidence in support of the null hypothesis. Then when you look at the coefficient of the variable called experience, this is the p-value. Notice that it is larger. So the p-value here is large. This is a large p-value because it is bigger than that. It is bigger than that. So that means that we have no evidence to reject the null hypothesis. We have no evidence to reject the null hypothesis. So that means that we shall not reject this statement. We shall not reject that statement. So that means that this regression coefficient here is not significant. Not significant. The effect of this variable, the effect of the variable called experience is not significant. But usually we say, on the contrast, we say that the test, we say that the effect of the variable code experience is not significant. But in the other cases, we say that the tests are significant. When we are rejecting the null hypothesis, or when there's evidence for you to reject the null hypothesis, you say that the test is significant. The test is significant. Okay. So basically, that's how you use the p-values. Clearly here, you're going to reject the null hypothesis and so on and so forth. So you can check in the class notes for more examples, and you use the output given there to make conclusions or to make decisions. So let's look at the confidence intervals for single regression coefficients. And we start by saying that from the fact that if you take beta j estimate, the estimate of beta j minus the hypothetical value divided by the standard error of beta j estimate, from the fact that this one has a t distribution, from the fact that this item here has a t distribution with degrees of freedom equal to n minus k minus 1, from that fact, we obtain the, this is how you write it, 1 minus alpha times 100% confidence interval for their known parameter bj's, for their known parameter bj's, as follows, or as these. So you say, I would like you to remember the way you define confidence interval for the mean and for the proportion in business statistics too. So we can say that, recall that the confidence interval for mu, for instance, is given by x bar plus minus, you can have a t there, then s out of square root of n. You can compute it like that. Or you can have this value as a z here. Okay. So where the first item always represents the sample statistic, then this is the critical value. And for any given level of significance, the critical value is obtained for a two-tailed test. So this value is obtained, is the critical value for a two-tailed test. That's why there is plus and minus. Then the last item here is always the standard error. So this is the standard error of the mean. Standard error of the mean. Okay, so there are those three items in the computation of confidence intervals. Even when we're doing the confidence interval for the proportion, we said that this is given by P, which is the sample value, the sample proportion, plus minus Z. Then here we have PQ over N square root. Okay, where this value here is the sample value, this is the critical value in the context of a two-tailed test, and this is the standard error. The same way, we expect something similar to that here. So here we say that the confidence interval for the beta j's is given by the estimate from the data plus and minus the t value, which is always in the context of a two-tailed test. So sometimes we put alpha over 2 just to emphasize that fact, multiplied by the standard error of the estimate of the regression coefficient. So that's the formula that we use to obtain confidence intervals for regression coefficients. Remember, the J's are taking values 0 all the way to K. Okay, so let's note that. Number one, when alpha, if your level of significance is 5%, we talk about we talk about 1 minus 0.05 multiplied by 100%, which is equal to 95%. So we talk about 95% confidence interval. We talk about 95% confidence interval. So when alpha is 5%, we talk about the 95% confidence interval. And using the same logic, we say that when alpha is 10%, we talk about the 90% confidence interval, etc. etc. Then the second note is that the t statistic or the t value given there, the critical value, used in the computation of CI, of the confidence intervals, is obtained from the t distribution, tables, using alpha over 2. That's for two tail tests. So you apportion the level of significance to both tails and the appropriate degrees of freedom. Degrees of freedom. And it's good for you to note that degrees of freedom in this context will be n minus k minus 1. So for you to obtain that critical value, this is a value that you read from the tables. You need to get alpha over 2, then you use the appropriate degrees of freedom. Okay. So how do we define the hypothesis when you're using the confidence intervals? So defining so let's look at defining hypothesis for the confidence intervals. Defining hypothesis for CIs. And we say that the null hypothesis for the untransformed data, okay, for the level model. Remember the level model? The null hypothesis for the level model is that the confidence interval, that is the upper confidence limit and lower confidence limit, contains the zero value by default. So that's the hypothesis that we test. By default, that's the hypothesis we test, that the interval that you have calculated up there will contain the number 0. For instance, something like this. You see, this is the upper, this is a lower, this is a lower confidence limit. This is the upper confidence limit. So we're saying that within this interval, the number 0 is found there. So that is similar to testing this hypothesis that beta j is equal to 0. That 0 will be found within that interval. Okay. Then the alternative hypothesis. The alternative hypothesis is that the CI, or the confidence interval, does not contain zero value. Does not contain the zero value. Okay. So 0 is so in this case we're talking about something like this. If this is your lower confidence limit, upper confidence limit, we are saying that either 0 is found here. You can, maybe 0 is somewhere there. So that means the others are positive, or it looks like this, or this is a lower confidence limit, upper confidence. So maybe 0 is somewhere there. Okay. So this is equivalent to H1, that beta J is different from 0. That is, does not contain 0. Does not contain 0. So the hypotheses being tested here are similar to the default hypothesis that we were testing earlier on for single coefficients. So if you're using the confidence intervals, you don't use the other method that we've discussed up there. So you can use them interchangeably because the conclusion will be the same. The conclusion will be the same. Let's have some example. So we consider a sample of size 506, which is a very large sample, and the output given below. So we have the intercept, we have a variable called Knox, and another variable called crime. And then we have the estimates, the standard errors, the t values, and the probabilities. So the question is, obtain the 95% confidence interval for beta 1 and beta 2. So using the above formula there, we say that the 95% confidence interval for beta 1 will be given by the estimate plus and minus 1.96. Because the sample is large, we shall not use the t distribution. We shall just use the normal distribution. We shall use the normal distribution. Then Victoria, I'll come to you. Then after that, we multiply that by the standard error, which is given in the output. Then you just simplify and get this. So this interval, if I were to represent it on a line, on a straight line, on a number line, it will look like this. So you find that 0 is not found within those two numbers. 0 is not within this interval. So that means that we reject the null hypothesis. We reject this hypothesis that beta J contains 0. That beta J contains 0. We reject that. Okay, because the truth is that, according to the evidence we have, is that the interval does not contain 0. So that means that that regression coefficient is significant. You will do the same for the other coefficient, that is beta 2, and then we'll see the kind of conclusion you're going to make. You can now use the previous tables that we have seen in our examples to compute confidence intervals for the given regression coefficients. Then you compare the conclusion you have when you use the confidence interval, when you use the p-value, and when you use the hypothesis testing procedure or using the critical values obtained from the tables. You will notice that the conclusion is the same in all the three cases. Okay, so that's how you obtain confidence intervals when the null hypothesis looks like that. You can also use confidence intervals for the general hypothesis. For instance, if you have a H naught that beta J is equal to some constant, and then H1 is that beta J is different from the constant, like that. So you will be obtaining your confidence interval in the same way we have obtained. But now, instead of checking whether that interval contains the 0 value, you'll be checking whether it contains this hypothetical value. You'll be checking whether it contains that hypothetical value. And then using that, you either say you reject the null hypothesis or you fail to reject the null hypothesis, depending on whether the interval contains this or not. So if the interval contains the hypothetical value, you are going to fail to reject. You will fail to reject the null hypothesis. But if it doesn't contain the hypothetical value, like for instance, if your hypothetical value is minus 200, or let's say minus 1200, it means that you'll be, for this interval, you'll be checking whether minus 1200 is found there. And you find that it is actually not found there. So you'll find that you're going to reject the null hypothesis. Be rejecting the null hypothesis. So you can generalize this kind of the application of confidence intervals to even the general hypothesis. But if you are using a computer, or let's say Excel, to obtain confidence intervals, by default, alpha is 5%. It is good for you to note that alpha can be another value. And then by default, the hypothesis that is being tested is this one. So if you are given a different alternative, then you need to set up, you need to be careful about it. You need to be careful about it. You need to be careful about it. All right, so I want us to move on to making inferences. We're still on inferences for the regression model. I want us to move to making inferences on all the regression coefficients simultaneously. So making inferences on all the regression coefficients using the F-test. So we start by saying that here the objective is to test the claim. So you test the claim that none of the independent variables, so that's the hypothesis being tested, none of the independent variables, you can sometimes call them the x's, affect the dependent variable or the y. So this is a claim or the hypothesis that we test in this context, that none of them is significant in explaining the dependent variable. Okay. And we continue by saying that the null hypothesis states that all the regression coefficients are equal to 0. That all of them, that none of them is significant, in short. That is, we define it like this: H naught, that beta 1. Remember, beta 1 is the slope, or is the regression coefficient for the first independent variable. We have not captured beta naught here. Is equal to all the way to beta k, and each one of them is equal to 0. So that means that we are doing this. Beta 1 is equal to beta 2 all the way to beta k. All of them are equal to 0. So this is equivalent to testing. This is equivalent to testing whether the model with intercept only, testing whether the model with intercept only, that is beta naught, is the correct model. So we are testing whether the model with the intercept only is better than actually the model containing all the regression coefficients. Okay. The alternative hypothesis is given by, so this is how you define it, is given by H1, and you say that at least one beta j is not 0, at least one of them. So if you get just one of them, which is significant, then you reject the entire null hypothesis. As you can see, the null hypothesis is a very strong statement that each one of them is insignificant. Okay. Then we say that the null hypothesis above, or the above null hypothesis, is tested by the F statistic. Called F statistic for overall, the F statistic for overall significance of the regression. So we use the F statistic for overall significance of the regression. Overall significance of the regression. And this statistic is, I think we have defined it in in one of our previous classes. Defined as this: SS explained divided by the degrees of freedom there for the explained variation, K minus 1, divided by SS residual divided by n minus k. So it's like the mean of explained sum of squares divided by the mean of the residual sum of squares. Okay. So which under the null hypothesis, is F distributed with k minus 1 and n minus k degrees of freedom for the numerator and denominator respectively. For the numerator and denominator respectively. So when we're using the F distribution, we have two sets of degrees of freedom for the numerator and for the denominator. So we have this. So these are the degrees of freedom. The divisors of each item are the degrees of freedom. So I'll be showing you the F tables in a short while, and you can see how to use them. But before you do that, let's say that the F statistic, this statistic is printed in the standard output, let's say computer output in regression analysis. But can be computed by hand, as earlier illustrated. In most of the cases, you'll be getting the computer output, but if you want to verify, you can just compute it by hand. All right, so let me display the F tables. So this is one page of the F distribution tables. As you can see, all the values of the F distribution are on the positive side. So 0 is somewhere here. So that is 0. So all the values are positive. And as you can see, it's a skewed distribution. Then if you want to calculate the critical values of F, so that's where you find it. Then this is your alpha. Okay. But you notice that there are two sets of degrees of freedom. So here you have the degrees of freedom for the numerator. And on the other side, we have degrees of freedom for the denominator. So the degrees of freedom for the numerator are running from 0, 1, 2, 3, 4. In the next page is continuing 10, 11, 12, all the way. Continues like that. The same case with degrees of freedom for the denominator, as you can see there. Continues all the way. Then here we have the different levels of significance. So the first one here is alpha is 10%. followed by alpha is 5%, followed by alpha is 2.5%, and so on and so forth. So once you know the level of significance and you know the degrees of freedom, just like we were doing in the case of T distribution, you will locate the critical value. For instance, if you are doing an upper tail test at 5% and you have 3 degrees of freedom on the numerator and 3 degrees of freedom on the denominator, you will come here. This is alpha is 5% and 3 degrees of freedom. Also here, 3 degrees of freedom, 5%. So this will be your critical value. So this is what will come and write here is your critical value, and so on and so forth. So basically, that's how you use the F distribution tables. Any question there? So let's consider this data. We have already used this data in our previous examples. Let us run a regression model of Y on X1 and X2. Then we observe the F statistic and try to make a conclusion about the overall goodness of this model, or the overall fit of this model. So like we did the other day, you need to go to regression analysis. Then this is the regression here. You say, okay. And you arrange for Y, your range of Y is that. And then your range of X is these two columns. Well, that is okay. Yeah, so that's okay. Then you can have your residuals there. You see now I can add the confidence intervals. Okay, this is 95% confidence intervals. Maybe I can talk about now 90%. I can change it. You can change the level of confidence. Then you have the residual plots, and that is it. So let's say, okay. So the output is here. So from this output, we have already learned how to explain the first part of the output, especially the R squared, the adjusted R squared. We have also seen how to interpret the information given here. As you can note here, I've changed the confidence interval, is also found here. You see, confidence interval, the lower and the upper values are found here. So the objective is to check whether this interval here contains the zero value, And you notice that from this lower value to this lower value to this upper value, zero is found in between, because this is -2, -0.2 to +6. So zero is somewhere in between those values. So this coefficient here is not significant. So it means that this coefficient here is not significantly different from zero. So it is not significant. The same case when you come here, you notice that the interval here contains the zero value, because this is ranging from minus to positive. In other words, any interval that captures the positive and the negative, it obviously contains the zero value. That means that you cannot reject the null hypothesis. You cannot reject the null hypothesis. Okay. Then in the last one, we have from -2 to +2. So again, so you notice that the regression coefficients here, all of them are not significant. So in this case, when we are testing the joint significance of all the slope coefficients, clearly you notice that each one of them is not significant. So we expect that when we go to the F statistic, that you remember the null hypothesis is that all of them, each one of them is equal to zero. It's not different from zero, which you expect to be true when we use the F distribution. So the F distribution uses the table here, the ANOVA table. This is a table that we have come across, the F distribution table, the ANOVA table. So the Excel gives you this one as regression, but as I've put in brackets here, this is what we are calling the explained source of variation. Then this is the residual. Then here you have the sum of squares explained. So this is SS. This is SS. So this is SS explained. SS explained. This is explained. This is this number here. Is this number, and then SS residual SS resid is this other value here, so equals to this value here, like that. Then the mean sum of squares is what is captured in this column. The mean sum of squares, let me remove this. So the mean sum, let me write them here. So the mean sum of square explained in this case will be given by the explained sum of squares divided by the degrees of freedom, 2. There are 2 degrees of freedom because k is 3. The number of parameters estimated is 3. You minus 1, you get 2. Then the mean sum of square residual or an unexplained residual will be given by this value here divided by the degrees of freedom, which is here 3. There are 3 degrees of freedom because the degrees of freedom for the residual is n minus k, where n is 6 and the k is 3. So you have that. So what you're calling f, which is given here also, is the ratio between these 2 values. So f statistic here will be given by, if you take this value here divided by this other value here. So that's what gives us the value shown here. That's what gives us the value shown here. So this is equivalent to the test statistic or the calculated value of f. And this is what we shall be comparing with the critical value of f, where the numerator degrees of freedom are 2 and the residual degrees of freedom and the denominator degrees of freedom are 3. So let's go to F tables and locate the critical value there. So here are the F distribution tables. And in this question, we shall be assuming alpha or using alpha is 5%. And the degrees of freedom for the numerator is 2. And the degrees of freedom for the denominator are 3. So we shall be working with this column. This is for the numerator. And then for the denominator, we are working with this. Then using that, we'll get the critical value is 9.55. Is 9.55. So that's what we shall be used to test the hypothesis. So if you are to sketch that distribution, we'll be talking about usually is a skewed distribution like that. Okay, so this is the F critical, which is 9.55, which is 9.55. Then you compare that with the calculated value, and the calculated value we saw is 3.21. Let's say 3.2. So the calculated value is here. This is the F calculated. So basically, this is the acceptance region, and this is the rejection region. So clearly, since F calculated falls in the acceptance region, we shall fail to reject. We shall fail to reject the null hypothesis. Remember, in this case, our null hypothesis looks like this. We have beta 1 is equal to beta 2 is equal to 0 because we have only 2 slope coefficients, or we have 2 independent variables. So we are trying to test that against H1 that at least, let's say either, because here I can say it like this, either beta 1 or beta 2 is different from 0. Either one of them. If there were 3, I would say at least one of them is different from 0. So here we are failing to reject this statement. We are failing to reject that statement. So we are accepting this statement. So like that. So that means, and this agrees with our output, because in our output we saw that all the regression coefficients were not significant. So this confusion here agrees with the observation that we saw there. Okay. Alternatively, you can use p-values. You can use p-values to check whether the observed value of f is significant. Okay. And I think we have the p-value in the output given there. So the p-value from Excel is called the significance of the statistic itself. So this here is the p-value corresponding to this f calculated value. And clearly, as you can see, this this p-value is larger than 0.05. So this is a large p-value. So we fail to reject. We fail to reject the null hypothesis. So you end up with the same conclusion as you saw there. Okay. So that's basically how you use the F distribution to test the significance of all the regression coefficients. And that marks the end of this topic and also the end of today's class. Let me know if there are questions. If there are no questions, we meet next week. Thank you.